Guys, welcome back to my channel. So today let's talk about regression models and a causal effect. Let's talk about how to use regression models to establish or to examine the causal relationship between X and Y. So I'm not gonna make a long video, like 16, 17 or 20 minutes long video. I don't want to bore you with that. So let's do it short, within 5 minutes. So this could be the lesson 1 of finding causal relationship using regression models. And we're focusing on the definition of causal relationship, causal effect, and how does that relate to the regression models, how we use regression models to understand the definition of causal effects. Okay, let's get started. Today, let's talk about the causal effect. So you should know that we use a particular experiment to define causal effect. So this experiment is called randomized controlled experiment. So the name of the experiment doesn't matter. So, but as the name suggests, the randomized, you should know that you want to find a causal relationship between X and Y. So X is an action, or we call it a treatment, or an action, or an independent variable, and whether X causes Y, and this Y is dependent variable or outcome variable. Right. So let's suppose X is a treatment. So we use the word treatment. For example, the easiest way to understand it is, let's suppose this group X equals 1, and this group, just for comparison, X equals 0. So let's suppose X is 1 is all the patients given drugs, and X equals 0, all the patients are given placebos, right? So you want to know what the effect on the outcome variable Y of being in the treatment group. So this is a treatment group, and this is a control group. Okay, so the treatment group, let's suppose I give you an easier example is, let's suppose X is 1 is the students in the small class, and X is 0 the students in the large class. So now the small class could be a treatment, and large class is just for control. And you observe student test score. So now in this group you have test score, right? Y1 all the way to yn1. So there's a number of observations n1. So in this group is y1 all the way to y sub n2. So this number of observations is n2. So for this group, we call it treatment group because all the students in the small class. For this group, it's called a control group because all the students in large class. Okay, if you want this to be a randomized control experiment, that means the treatment, whether it's small or large class, the treatment, we can write this treatment, is randomly assigned. So treatment is randomly assigned to make sure that the only difference between treatment and the control group is the treatment itself. So there's no other difference between two groups. So we call this experimental data. For example, you have 100 students. So you randomly select 50 students and make them sit in the small class. Make them sit in a small class. Okay. And the rest of 50 students, just make them sit in large class. So you just the treatment is randomly assigned. So this is based on this, we got experimental data because this is experiment, right? You observe, let's suppose this is experimental data, right? This is our experiment. You observe for this group, you observe their average test score. In the small class, maybe it's 90. And for this group, you observe the average test score maybe is 80. And then the difference, right? The difference changing average score, the difference in test score between the two groups is 10, right? 10 points. And because the treatment's randomly assigned, so you can say that the reason you observe the 10-point difference in test score between treatment and control group is because the treatment itself. So randomly assigned means there's no correlation between the treatment and any other determinants of test score. We can call it any other determinant test score error. So this is experimental data. To understand that, you can compare it to observational data. So this is we can write experimental data. Okay? And this is observational data. Based on observational data, we observe that, right, this many students, maybe this 500 students in a small class. and this many students in a large class. And we observe that this many students, average score is 90. This our observational data is 80. And then we know the difference is 10. And the thing is, we can't make the conclusion that the reason we got 10 points difference is because of class size. Why? Pause this video, think about it. Because maybe there's some other difference between the two groups. Maybe in this small class, right, this group of students in a small class, maybe their family income is a lot higher than their counterparts. So that means family income is higher, and then their parents give the students a lot of outside school learning opportunities. Right? This group of students, the average family income is lower. They have much smaller learning opportunities outside school. So the reason you get a difference in test score is not because they're in a different class size, right? Not because the class size, it's because they're difference in family income. Based on observational data, the treatment is not randomly assigned. So we observe that maybe the students, only 20% of students English second language, or they're immigrants, English second language. Maybe here, 80% of students English second language. So now you observe the different test scores not because of the class size, it's because the English is now their first language. So let's suppose this is in the school in the US. So the thing is, based on the observational data, we can't guarantee that the only difference between two groups is the treatment itself. So that's why, even if you observe the difference as 10 points, you can say that's caused by the class size X, maybe caused by some other variable, income, and whether you're immigrants in English second language, or by some other confounding factors. We call this confounding factor. So maybe this is the reason we get this difference in test score. Maybe this is the reason we got the different test score, not the class size. Okay, so randomized control experiment, if the treatment is randomly assigned, you randomly assign small class to some students, a large class to some students, and then you can ensure that the only difference between the two groups is the treatment itself. Okay, and then you observe any difference, you can say that's caused by that only difference. Okay, you have the control here because you have a treatment group and you have control group. So you can control for your experiment. So that's why we use this randomized control experiment to define causal effect. Okay, again, the causal effect is defined to be the effect on an outcome of a given action or treatment as measured in an ideal randomized control experiment. Okay, because in such an experiment, the only reason for the difference in the outcome variable between the treatment and control group, right, is the treatment itself. Okay, now let's look at how this related to the regression analysis. So if we use X is a test score and Y is test score, X is class size. So now Y is B0 plus B1X plus error. So you should know what's the inside error. Right, that's kind of key in the econometrics class. One of the most important concepts. You should understand what's inside error term. Okay, so what's inside this error term? So error. So this is a test score. It's determined by. It can be explained by the model, and it can be explained by error. Right, error include all other determinants of test score, which is Y. For example, family income. For example, whether English is second language. Right? For example, how many hours you study, or parental involvement. Let's suppose this is a small class. The parents' educational background. The parents are very strict. Right? Parental involvement is a lot more than the parental involvement in this group. So now the reason you get 10 points difference is not because of class size, it's because of how strict the parents are. So now the error stands for all other determinants of Y, because this Y is a function of this plus error. So if this is a randomized control experiment, that means there will be no correlation between the treatment and all other determinants of y. In other words, expected value of error given x is 0, is constant. And because you have a intercept here, so we call that the first least square assumption for causal inference is expected value of error given x is 0. So this means there's no correlation between x and other determinants of y. This is most important, most difficult condition to satisfy in order to make a causal conclusion or make a causal inference for B1. So this is the first least square assumption for B1 to have a causal interpretation. Okay, so that means there is no correlation between x and other determinants of y. Basically, that means it's kind of as if a randomized control experiment. Okay, so make the video short. Let's stop here. And for tomorrow's video, let me give you the further explanation of this. Okay, and what the difference between expected value error equals 0. These two things are totally different. Okay, this is always true because we use OLS, but this is only true when there's no correlation between other determinants of y, error, and your most important or variable of interest, x. Okay, this is only true when there's no correlation between x and error, but this is always true because we're using OLS to get the B0, B1 estimated. Okay, so yeah, let's stop here and hope you find that helpful. Hey guys, hope that makes sense to you, and stay tuned. I'll make more videos on this topic, how to find the causal relationship, how to examine the causal relationship between x and y using regression models. And again, thank you so much for watching and support and everything as always, and see you in the next one. Bye.